to represent the nucleus, so I'm going to represent nuclei by lines, thicker lines, double lines, like this. This is an electron, that's a photon, and this is a nucleus. A nucleus, let's say to take a hydrogen atom, the nucleus is just a plain proton. And it looks fat because we don't understand it inside there. But the electron is nice and thin, and it goes along, and nucleus might emit a photon which interacts with the electron. It could be that over 1 million years, or a few millionths of a second in the practice, that you can emit several times photons back and forth, and the electron in general does some sort of a dance like so around the proton. Calculate the total amplitude, an electron and a proton down here. Still looks like an electron and a proton after a long time. You have to add the possibility that the electron and proton just went directly with ease, or that the electron went for a while and there was an exchange and another one of photons. Both of these things happen, and the interference between them has an effect on the motion of the electron. In the presence of a proton, an electron does not move the same way as it does when it's in empty space or free of a proton. When it's free of a proton, the amplitude to find an electron at a certain point is given by this function. As a matter of fact, you can show, in a manner similar to the case of light, that if there's nothing but an electron in the space, it appears to go at a uniform speed in a straight line. That is through the interference, of course. The same way with light. But when there's a proton in the neighborhood, or any other source of photons, but let's take the case of a proton. As the electron is moving, its amplitude keeps changing because the amplitude of the situation keeps changing because of the exchange of the photons. And the result of that is that the amplitude to find an electron anywhere is altered by the possibility of exchange of photons with the proton. And that is all computable and quite complicated. That's the theory of atoms. But if we have a very large-scale event in which things are far apart, and I drew it somewhere, but it's long lost, if I have some metal plates with an excess of protons here and some extra electrons sitting here, then an electron going along here, and mind you, this is on a very large scale compared to my other drawings where atoms were big there. Now they're tiny. There could be a photon go across here, another photon, another photon. These billions of photons going across are all very long wavelengths, a few centimeter, half a centimeter, contain very low energy and hardly disturb the system. The thing that's emitting them can emit them without any change. It's such a small energy. At any rate, the main point is that the electron in going along in this space here is not going along the same way as it would if there were no plates. And when you calculate the chance of finding an electron to go from here to here, you'll discover also, just like we did with light, that in this approximation of large scale, the only path which is important is a special curved path, not straight, because the photons are altering the amplitude. Actually, yes, that's right. The interference, I got the curvature in the right direction. That's what was worrying me. In the case of light, you remember that there was an angle at which the amplitudes came in, and if we added all these amplitudes together at slightly different angles, the only path that was important was one in which the angles are not changing. In the case of light, the angle depended only on the time. And so it was the time should be not changing, or least. In this particular case, the quantity which is not changing is more complicated than the time. It's a more complicated thing. It happens to have a different name. It's called the action. And the pairs of particles can be calculated by computing a certain quantity on a path called the action, and the path takes the curve, which looks like the curve of least action. This way of putting the laws of mechanics was discovered many, many years ago as what we call classical mechanics. The relationship of quantum mechanics, quantum mechanics is exactly right. And the classical mechanics is an approximation. The behavior of light jumping all around as before is right. But the idea that it goes in a straight line is an approximation. The idea that an electron goes in a curve is an approximation. It's really amplitude jumping about. This example, however, shows something interesting. In many circumstances, it's true that we have long wavelength photons which can be emitted because they contain so much little energy without disturbing the source. And whether or not they're absorbed by an electron is a matter, it doesn't make much difference to the energy of the electron. And so we can find an electron moving in a region in which there are available many photons, enormous numbers. The wavelengths are so long, the energy is so low, the numbers are very large. But they're all about the same. Then we can describe this electron by saying it goes in a straight line except it's disturbed. It's disturbed by the possible presence of photons. We say, in an old-fashioned language, that there's a field in the neighborhood, an electric and magnetic field, which alters the motion of the electrons. But what this electric and magnetic field is amplitudes to find photons in very large numbers under circumstances where their energy is so low that it's easy to emit them. And that's the earliest ideas then about the motion of electrons was that they were particles being bent by forces generated by fields. This is now all passé. Instead of that, it's just the exchange of electrons, exchange of photons between the electrons or between a nucleus and the electron, the amplitudes for which are all given by this little constant, and the amplitude for the photon to move is given by a known function, and the electron likewise. And that's all there is to it, and from it all the rest of the laws of physics come out. Another example is the scattering of light. Light, according to that view, would always go in a vacuum in a straight line, or however it goes in a vacuum. And if the distances are big, it would look like a straight line. But we know that we've talked many times about light being bounced and reflected from the surface, or light going slower in materials and so on. I have to explain that. What's involved there is that in matter there are electrons, and if this is a typical electron moving along, again, time is this way, unlike this diagram. This is an ordinary diagram moving through a piece of material. We're moving through some plates. But here's time again in space. We can have a photon coming in from the outside, hitting an electron in an atom, say, or anywhere. And after that, a photon is emitted by the system. So a photon comes in and a photon goes out, and it's even possible that the electron's condition that was before is restored again, although temporarily it's been changed. Of course, if you like this game, you can imagine another diagram. Let's see. Another possibility, crazy idea, isn't it? That it's emitted before it's absorbed. Yes, you add that too, both together, and it comes out right. Don't worry about anything, just add everything. It's only the sum of these two which is the right answer for the scattering of light. So you see that when we have electrons present, a photon can come in and come out in some other direction. That is the basis of the rules that we made before. And I should, for completeness, repeat these rules and explain them all over again, because in this system I had a different rule. I talked about photons having an angle dependent on time, and everything was kind of funny, and it doesn't look like it here. So I have to explain that just a little bit. It works more detailed. Now this is a more detailed description of what happens in here. First, we were supposing that we had monochromatic light, that is light of one color. That means that the source was emitting light of only one color. How does it do that? The way it does that, what that corresponds to, a source emitting light of one color, is this. A source, this is time again, and this is space. And let's say the source is standing here. It's like this. It might have emitted the photon then. It might have emitted it later. It might have emitted it later. It might have emitted it later. The amplitude to emit it at each time is different. So the amplitude to emit the photon at different times from the source is changing. It's going around backwards. Yes, backwards. Like so. Now, to make a quick idea of it, let us suppose, for simplicity, that this function for the photon, just for simplicity, only, for instance, right at long distances, only connects 2 points which are going at the speed of light. It's a simple model. It's a simple approximation. So if I were to come over here and get the if I would get the photon to get to here by one route and compare it to another route, when the time is longer, it must have been emitted earlier. If I asked for it to arrive here at a certain time, if it came this way, it was emitted at one time. If it came this way, it was emitted at another time. The amplitude to be emitted earlier. It's going around backwards with time. Yes, so the amplitude to emit it earlier has a bigger angle. That's why the one that takes longer has the bigger angle. It's not really a property of the photon in the space, like I cheated you in making believe it was. It's really the amplitude of emitting. If you get the photon at a certain time here, it means that it left here earlier. If it went this long route, it left even further earlier. And if this source was emitting with an amplitude which is changing in time, then the amplitude to arrive here by this route and by the long route are different because the source was different. So it's really due to the source that there's a difference in the phase, or the angle rather, of arrival of the light. In addition, there's one other thing wrong. I talk about light being reflected from a surface, and that's just nonsense. It's not reflected from the surface at all. What it really is scattered by the electrons in the material. So the correct picture of this thing is this. I'll draw a better picture. What really happens is that the light comes down and hits the first piece of matter and then is scattered back by that kind of a picture on the last board over there, down here, in microscopic view. Or it comes down here and is scattered there. Or down here and scattered there. And that's all it's done. It's really scattered in the inside, not on the surface. And so we have to add together a whole lot of amplitudes, each of which takes a little longer and have come from the source at a different time. And so it ends up adding a whole lot of little arrows. Each one is a little turned relative to the other by about the same amount. And if you add arrows, each one of which is the same length, and they're turned relative to one another, you go around on a polygon, or if the arrows are very small, a circle. And so you see that the net result, for example, of a certain thickness is to have an arrow, a net arrow, from this end to here. By the way, if this is the center of the circle, that could be represented as a resultant from these two, this and this together. But that's the way I cheated last time. I just drew these two. So what really was happening was the circle. Let me explain it again. It goes, each little contribution in the interior goes around in a circle. And if I have the thickness just right, exactly right, the circle is complete. And the net result is 0. That's the first minimum. If I go a little thicker, it goes around again and comes back to 0. If I used half its thickness, it would go around halfway and stop. And in that case, I get the biggest possible amplitude, and so on. So those fluctuations were really not from the surfaces, but from the interior. At least we have the glass where the matter is doing the scattering of the light, and not some imaginary stuff like the surface. I cannot resist. One of my problems is, the problem is with this is that I can make it more interesting by showing you how more and more of the phenomena that you ordinarily see work out this way. And at the same time, I have a desire to tell you about all of the phenomena which are quite unlike what you see, which are quite unexpected and exciting. And I don't know which to do, either to convince you that it's interesting because it's something you didn't understand before, or it's exciting, and the thing to do would have been to give 8 lectures. But I didn't. I only contracted for 4 lectures. So what I've decided to do this time is to tell you about something unbelievable but still true, which is very interesting. So it doesn't explain the phenomenon you know about, but it explains something you don't know about. And that's this. Let's take the simple situation. Well, there's many possibilities. I'll say it very neatly. In that we would talk about a photon going from a place to place, and that we could also have it this way or turn it around. We could have the points 5 and 6 being definitely later than 5, 6 being nearly the same time as 5, or 6 being earlier than 5. And when 6 was earlier than 5, it was just a photon going the other way, if you'd like. Now, as it turns out, the same thing. Mathematical form of these functions is very closely related. I think I already told you, if I didn't, I meant to, that d of 2 and 1, if I put 0 in for the mass, that f of 2 and 1, if I put 0 in the mass, is the same as this d. So all the functions are exactly the same, with just one number in them, 0 for the case of the photon. And their properties are very similar. So at first you thought everything was understandable when I drew a picture like that. For example, the electron's coming along, the photon comes, electron goes to another place, and the photon comes out. I did shock you by having the photons come in the wrong order, but it's still all right. But this is a real good one, isn't it? Suppose this point here gets earlier than this point, and I start to draw something like that. Never mind about all the photons, they're in there too, but the point I'm trying to emphasize is the motion of the electron. This is time, and this is space. Question. If this point is called 5 and this point is called 6, and 6 is earlier than 5, I hope to goodness this f is 0, huh? Because I don't want things to go backwards. But it isn't 0. What it says is that this is perfectly possible. And what can it be that's going backwards here? Oh, you say that's easy. It's just an electron going from here to here. Almost. Almost. It's this way, though. The electron carries a charge, and it's good to put an arrow on to remember which way it goes. In this particular case, the arrow is going the wrong way. And it turns out that this section going backwards has many properties exactly the same as an electron, but it's not exactly the same as an electron. It is possible, by getting enough energy, so on, to get an isolated long piece of this backward moving section. See, it goes on for a long way. Maybe it's connected to an electron this way and an electron that way, but it's got a lot of things happening, photons coming in and photons going out and so on, except it's going backward. You can take a piece of that line and put it between those metal plates that we were talking about, and it curves the wrong way. If you figure out which way the amplitudes are coming and they're changing, it'll turn out that it'll bend the other way. It moves toward electrons. In fact, it's just like an electron, except it's positively charged. It's called a positron, and it really exists. It's easy to make. If you get enough energy with some photons in a field and stuff, you can produce this kind of a situation. For instance, you can take this and have the following physical possibility. I need more blackboard all the time. Let's see what happens. Yeah, I want that one for later, so I have to have this one. Good. For example, if I drew some terrifying thing like this, with 2 photons, this represents the possibility that an electron and a positron initially in space come together, disappear. No more electrons. Time is this way. Time is this way. Yeah, I know. It looked like I drew the diagram sideways. I didn't draw the diagram. They get 2 photons out. An electron and a positron can annihilate and emit two photons, directly observed easily in the laboratory. Or photons can come, I can draw it the other way. Photons can come together and produce that. Produce an electron and a positron pair. So that it turns out, because of this mathematical business, that every particle can go backwards as well as forwards in time if you want. And so for every particle in nature, there's another particle that goes with it matched, which is called its antiparticle, and which has many of the properties of the original particle, with some of them with the sign reversed. In the case of the positron, for example, its mass is exactly equal to that of an electron, comes from the same function, and its electric charge is opposite in sign. That you can find out by checking some numbers in here. It's all the consequence of these rules. In the same way, there are antiprotons and so forth. And a proton and antiproton can come together and annihilate each other, producing a lot of other particles. For instance, they could produce two gamma rays, but it's rare, but it can happen. The other particles I don't want to mention because they come next time. And so we have the possibility of having any kind of combination of these things in space and time, sometimes going forwards and sometimes going backwards. The backwards one's a positron. When a positron is actually made, the way I described there, in the laboratory on the Earth, it doesn't go very far before it disappears because it finds an electron and the two combine, like the first picture, and two photons come out. But you can make them, see them go, deflect them with plates the wrong way, and they annihilate again. They were predicted by Dirac from the theory he had, which was really a calculation of this function for the first time, and discovered very soon afterwards by Anderson in the laboratory. This also permits, well, let me now finish. Well, I don't know if I have finished. Yes, not finished. One thing I can't resist. This minus sign is so interesting. It means that when you cross up which is which, you have to subtract the amplitude. And that has an interesting consequence. Suppose the 2 points 1 and 2 are very close together, that you want to emit two electrons in the same condition at virtually the same position at the same time. So if 1 and 2 are the same, put 1 here and 1 here, and 1 here and 1 here, because 1 and 2 are the same place and same time. Now you see that this expression differs in no way from this, and therefore the difference between them is 0. That means you can't make two electrons, or you can't expect to find two electrons anytime where they're made at the same point in the same place, same time at the same place. Or if you try to put 3 and 4 at the same point, you see if point 3 and point 4 are the same, these cancel. That would mean that two electrons can never be found at the same place at the same time. It turns out what it means is that they try to stay away from each other. Not just because of the exchange of photons, which is one influence which does make them stay away from each other, but by a completely different thing, which is this interference of the amplitudes. Actually, because of the fact that there are polarization cases, it turns out what I said is right, but if you take into account the polarizations also, then you can make two electrons at the same point, but they must be in different conditions. One must be polarized one way, and one polarized the other, so that you can still keep track of which was which. So as a matter of fact, you can get two electrons into the same condition of, not just, you can put two electrons into the same condition of motion, one polarized one way and one polarized the other way, but that's all. You can't put any more. It is on this fact, with its consequences, which is one of the other things I'm unable to show you because of lack of time, the very beautiful fact that all of the chemical properties of substances can be worked out. If we start with a nucleus which has some protons in which are attracting electrons, we start with one proton and it puts one electron or around it. If you start with a nucleus which has two protons in it, it's called a helium nucleus, then you can put one electron around and put another electron nice and close in the same place. They try to get as close as they can. The other one can be in the same place because of the two possible directions of polarization. Now when you take next nucleus, number 3, and you want to put 3 electrons around it, one goes in nice and close, the other one goes in nearly the same place but polarized the other way, and the third one, because there's only 2 ways of polarizing an electron, can't be in the same condition as the other 2 and has to be wander around out here waiting to get in. It's not repelled by any electrical force, it's just repelled by canceling amplitude, by interference. It has to stay out there. It's easy, since it's far away, the photons which it exchanges with the nucleus have small effects. It's easy to remove it. The last electron, in other words, is easy to get off. And that represents an atom which is chemically much more active than helium, because it's easy to remove an electron. It gives an electron up easily. Such a thing is called a metal. In fact, when you compress a whole lot of these atoms together, the electrons are so easily outside one. They're so easily removed that they just swim around in a kind of sea around the nucleus. They don't even stick on one. They wander off to another one and they wander off. They wander all around inside, but 2 of them on each nucleus is still there. Boom, 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 but one extra ones are wandering around. Such a material, with very little electric forces, you can make all those electrons shift one way or the other. There's electrical conductor. And that metal I'm describing is lithium. It's the first metal. The element before is helium, and it's hard to get its electrons from the inside. Helium is chemically almost inactive, and lithium is chemically quite active and makes a metal, and so on and so on. I am very sorry to have such a brief time to explain phenomena that you know about in terms of these ideas, as the ideas are by themselves are rather difficult to get at, and I wanted to be complete in telling you about the most mysterious aspects rather than cheat by leaving out something important. I guarantee you, aside from the polarization, which is not important, I have now left out nothing, and the whole theory of electricity, electrodynamics, our understanding of the world comes from just these pictures. Each picture is interpreted this way. When you draw a picture, you write an amplitude for this, and this, and multiply it together, wait, and 2 C's to cut it down. Finally, I would like to describe the motion of an electron in going along. Here's an electron all by itself going from point to point. All right, nothing to that. But it has to be corrected. It's also possible that as the electron was, instead of just going directly from point to point, goes along for a while, decides to emit a photon, and then horrors, it absorbs its own photon. Something perhaps immoral about it. But it does it. All right, it might not be the nicest thing to do. It does this. And just, you understand what this symbol represents now. If you put some points in here and label these, there's an E for this, an amplitude for that, an amplitude for that, an amplitude for that, all multiplied, for the amplitude for this electron to go from here to here, times the amplitude for the electron to go from here to here, times the amplitude for the electron to go from here to here, times the amplitude for the photon to go from here to here, times C, times C. Those are the couplings for the junctions. And that bunch of junk all multiplied together has to be added for every place that this can be and time, and every place and time that can be. And when that's all done, you've got this piece, which is supposed to be added to that piece. Now when you add this piece to that piece, you find that the motion of this is slightly altered. Its behavior in particular in a magnetic field is changed. In a magnetic field, if the thing was as simple as this, it turns out its polarization changes at a certain rate, or its spin changes, at a rate that can be measured, and which we'll call 1. 1 is the result you would get for this alone. If you add this to this and figure out how the thing moves, it behaves in a magnetic field slightly differently. And if you just add this, you get 00116, or 8, or something like that. If you're this time, for the fun of it, I'm going to write the formula. It turns out that this term is proportional. The contribution in the magnetic field of this is proportional to 2 C's. C squared is 1 over 137.046. Oh, sorry. Well, I learned the error. I'm within the error. over 2 pi. This time it's easy. Our students learn how to do this calculation in their elementary course in quantum electrodynamics, which is a third-year graduate course. All right? This was worked out by Schwinger for the first time in 1948. The next case is to take diagrams corresponding to 2 of these things, something like this. There are other possibilities. Let me erase here and write the other possibilities of this. I'm just continuing. There are other possibilities, all of which involve 4 C's, C4 sometimes. And there are other things that can involve 4 C's, are something like this. Okay, there's a different kind of connection timing. And finally, there's nothing significant about that being straight. These points, it should be, you know, and stuff like that, but I'm too lazy to draw it cockeyed. Here's an interesting possibility. Photon is emitted, makes a pair, electron and positron, and again, if you'll just hold your moral criticism, the electron and the positron annihilate again. So there's an electron going this way and a positron going that way, and they annihilate again into a photon, and that comes back. It's called a closed loop. It comes and it goes. This involves 4 C's, 1, 2, 3, 4 also. And this, and this, which involve 4 C's, can all be added together, and you get something proportional to C4, which, by the way, is fairly small, being the square of 1%, which is 1 in 10,000 or so. And the coefficient, this time it's not so easy to write down. It's 0.03 something something. All right. At any rate, this took 2 years to calculate after this was worked out. And it took 1 year to find a mistake in that calculation. It's true. It's true. It was very exciting because it was calculated very carefully by 2 different people. They thought they were independent, but they compared a little bit or something. They both had the answer was wrong, and it disagreed a little bit with experiment. And they improved the experiment, and it disagreed, and it showed that quantum electrodynamics was wrong. No, it was an error in arithmetic. So everything was all right. And now, that was 2 years later. That brings us up to about 1950, 51. And now we go on and we try to do 3. Oh. Well, you see, when you have to add all these possibilities, you get lots of pictures, of which I'll draw one more, but you can keep on going and draw a lot more. You make a pair, they interact by exchanging a photon and so on. And each one of these diagrams represents a definite formula, and we use the diagram to represent the formula. And we just make these pictures, write down what they correspond to, and add the amplitude. A straightforward cookbook process. All you got to do is write the picture and translate things and write the factors and add everything together. Therefore, it can be done by machinery. Now that we have super-duper computers, we've got so we can compute this one, C6, and by that time it's down to the millionth part. And altogether, so far up to today, as I told you in the very first lecture, this number comes out to be, when you add all this stuff together, don't stop here, but keep on going, 596523 plus or minus 3. Calculated and experimental is 24 plus or minus 2 at the present time. What do we got to do to make it better? Some of this error is that the computer who did this calculation only did it approximately, and we can do it more exactly by using more time on the computer with a little more money. That'll improve the error for that. However, there's no use doing that until we look at number 4. That is C8 with 4 of these extra 8 couplings in it. And people are just beginning to see if they can estimate how big the C8 term will be, because that will be of the same order as this error. In addition, there's an error that comes from the fact that when we go to calculate it, we got to put a number in for C square, and this is as accurately as it's been measured up till now, and a part of this error is due to that. So I have to wait to give this lecture again, perhaps in a year or 2, in which case I'm sure I could write one more figure here, and the error would be smaller. But the question I am not sure of course, is whether it will still agree with experiment. That one never can tell until one makes a calculation more elaborately. I think then that describes the framework of the world as we see it. In the first place, amplitudes for every event that we add together when we expect to add probabilities, and we multiply when we expect to multiply probabilities, but we're not doing it with probabilities, we're doing it with amplitudes. This makes us philosophic difficulties, if you wish, but after a while one gets used to it. One can think about these amplitudes, one can think about adding them, one can consider these as alternatives which you simply add as amplitudes. And after a while one gets to be quite familiar with this strange language. The ordinary experiences of nature, such as light going in a straight line, the conservation of energy, and so on, are all very easily deduced from these principles, and all there really is that we can find to all the phenomena that you see every day, with the exception of radioactivity and gravitation, is just the 2-3 rules. That a photon has an amplitude to go from one point to another in space given by a special function P. An electron has an amplitude to go from one place to another by another function E. And that there's a junction possible between a photon and 2 electrons, which has a coefficient which is a certain number. This slightly modified by a couple of cases for polarization, but no more really complicated than that, represents the whole sum of a knowledge, a summary, a most marvelously unified theory of almost all common experience, but not all. And therein lies the puzzle. There are much more in the world than just electrons and photons. There are the nuclei, protons and neutrons, and so forth. And the theory is therefore not a complete theory of the world, although it is, as far as we know today, a very complete theory of common phenomena. Colors, light, X-rays, positrons, electric currents, electric and magnetic fields, X-rays, radio waves, and so on, substances, hard and soft, chemical interchanges. Some atoms are easy to combine with others and some are inert. All of this is a consequence, as a result of this analysis, of first finding the right framework, which is the most exciting part of it because it's so utterly strange. But after finding the framework in which to describe things, namely amplitudes, to discover in the end only 3 amplitudes that you need to discuss. One is a simple junction number, and 2 functions, both of which, by the way, are really the same function. In one you put one value of m, and the other put the value 0. So next time I'll discuss the rest of physics and also all the puzzles which are still left in this theory if you thought that was absolutely complete. We still have a question or two to ask about it, and I'd like to describe that and other things in physics for the next lecture on Thursday. Thank you.